On January 27, 1944, a German V-1 flying bomb struck South London. Today, a modern drone hovers over a wheat field in Haryana, identifying nitrogen-deficient crops with multispectral imagery in real time. That V-1 was a guided projectile, blind to its environment. It relied on a preset gyroscope and a mechanical fuel cutoff to drop the weapon at a calculated distance. There was no camera, no sensor, and zero active decision-making on board. Since 2020, we have seen drones transition into autonomous agents. They can now navigate dense, complex environments without GPS, tracking specific objects and coordinating in swarms without human intervention. This autonomy is possible because the machine no longer waits for human commands. Advances in computer vision and edge computing allow the drone to process data locally and make navigation adjustments in milliseconds. For organizations, this represents a shift in strategy. Evaluating a drone based on its flight time is a metric of the past. The real value is in the software platform that resides within the machine. To understand that value, we have to look at the hardware stack, a linear progression from physical structure to digital infrastructure. A drone is a system of highly constrained, interdependent subsystems. Every mechanical choice, from airframe material to motor torque, is a response to the physical limits of unmanned flight. Mastering this stack is the only way to forecast enterprise capabilities and manage the supply chain risks that come with intelligent aviation. The foundation of the stack is the airframe and propulsion system. Unlike fixed-wing aircraft that generate lift through forward motion, a multi-rotor drone is naturally unstable. It maintains a hover by burning energy at an aerodynamically expensive rate. The primary bottleneck of drone performance is the battery problem. Modern lithium polymer batteries store roughly 250 watt-hours per kilogram of energy. Aviation fuel stores approximately 12,000. This 48-fold gap explains why advanced commercial drones reach their limit in minutes rather than hours. Drones use brushless DC motors and electronic speed controllers, or ESCs. These systems provide the high power density required to keep an unstable airframe level. Specifications let a kV rating, which measures RPM per volt, and stator size dictate the drone's performance profile. A platform can be built for speed, torque, or efficiency, but it cannot be built to escape the energy density of its battery. Because flight time is strictly capped by the current state of battery chemistry, hardware supremacy is a plateau. Since endurance is bottlenecked, a drone's strategic value is defined by the quality of the decisions it can execute within that brief flight window. Those decisions are managed by the flight controller, the brain of the drone. This computer reads sensor data and sends micro-adjustments to the motors hundreds of times per second. It is the only thing preventing the quadcopter's natural state if aerodynamic collapse. This layer is divided between open-source ecosystems like ArduPilot or PX4, which favor customization, and proprietary systems like DJI, which offer a closed, integrated experience. For the drone to do useful work, it must interact with its environment through the third layer, sensors and payload. The basic navigation suite includes an inertial measurement unit to track movement, a barometer for altitude, and GNSS receivers for global positioning. In environments where GPS is blocked or jammed, engineers rely on sensor fusion. This allows the drone to maintain its position by combining data from multiple onboard sources. Key technologies for sensor fusion include LiDAR for obstacle detection and optical flow cameras that track ground texture to ensure a stable hover. While navigation sensors keep the drone airborne, payload systems are the primary engine for data collection. Payloads range from multispectral agricultural cameras to thermal sensors for inspections and gas detectors for industrial leaks. The airframe is a delivery mechanism. The strategic value of the drone lies in fusion algorithms and the payload software that captures high-value information. The final stages of the architecture connect this autonomous agent to the broader enterprise. The communications link uses radio, 5G, or satellite to transmit processed data from the edge to the operator in real time. The ground station has evolved from a simple remote control into a data ingestion hub. It bridges the gap between the drone and cloud networks for immediate analysis. At this stage, drone hardware officially integrates with traditional enterprise IT infrastructure. This specific hardware stack reveals where the global technology supply chain is most vulnerable. China currently dominates the production of the components we just examined. the brushless motors, the speed controllers, the batteries, and the camera gimbals. Manufacturers like DJI utilized deep vertical integration of these subsystems to create cost advantages and quality control that competitors struggle to replicate. This concentration led the United States to place dominant manufacturers on entity lists, restricting their use within government agencies and sensitive sectors. Emerging responses, such as India's production-linked incentive scheme, are designed to build indigenous manufacturing for these critical subsystems and reduce dependence on a single region. Sourcing a drone now requires deep, component-level supply chain visibility to navigate these geopolitical restrictions. A drone is a balance of physical constraints managed by computational layers and sensor fusion. Real competitive advantage belongs to those who treat these machines as nodes within a software ecosystem. Organizations should no longer judge a drone based on raw aerospace specs like speed or weight. When these hardware layers converge with 5G and satellite networks, the sky functions as a coordinated, intelligent data network. By integrating these autonomous nodes into their digital strategy, leaders can move from simply collecting data to making automated, real-time decisions at scale. Those who see the AI node rather than the flying machine will be the ones who lead the next phase of the digital economy.